Okay, so hello everybody. My name is Matt Hanson. I'm the geospatial engineering lead at Element 84, and today am going to give an intro to STAC. Some of you may have actually heard bits of this presentation before. I've given variations on it a bunch over the few years. I'll talk about a background of STAC and the core specification and extensions, and then a little bit about the API, and then I'll talk really briefly, I'll just rapidly go through some slides on adoption on the software ecosystem, because a lot of that is being discussed in different lightning talks throughout today and tomorrow. Before I go into the STAC background though, just briefly some thoughts on cloud native geospatial. Of course, this is the main premise of these days, and so I'm not going to go into a definition about what this is. I think we all agree and understand what cloud native geospatial is. We're doing complete workflows performed in the cloud. I want to underscore though, like other things that this really promotes, and it's not just scalability, but we also have this reproducibility. So in science, there's a real reproducibility problem in general that has sort of been around for a while. And it's even more so with geospatial data because of the scale of the data that needs to be processed. And so historically, when scientific papers have been published, they might have run their analysis on a handful of data, but that data is unavailable, or it's just impractical for that analysis to be reproduced by others. And so things like STAC and tracking metadata and provenance, which is work that's ongoing in developing those standards around that, I think really have the potential to really help out this problem of reproducibility by allowing people to publish online their papers. So I've heard this term before of executable papers. I really like this idea where you publish your paper and it's an executable form where somebody can push a button and they can open it up in their own account and they can run the exact same analysis that you did and then also tweak things as needed. So to support this, I think that this is a better way to think about things as algorithm developers. If you're an algorithm developer and you're writing things, stop writing algorithms that actually operate on files. This is really generates a whole lot of mess in code, I think. It makes tracking provenance exceedingly difficult. When you write an algorithm that takes one file and outputs another file with some arbitrary name, no one is going to be able to go in and look and see what you did. So rather than this idea of operating on files, operate on metadata. So forget about the data, forget about where the data is located. And instead, the input to your workflow is metadata. And obviously, this is going to be STAC. And the metadata contains a complete characterization of the data, including where that data is and how to access it. And during your workflow, you're actually operating on that metadata. You are adding things to the metadata or changing things to the metadata, and you're fetching data if you need to, and any derived products or anything that you create, you upload and you put the location in the metadata, and your output is metadata. So it's not data in and data out, it's metadata in and metadata out. And this I think, is a really powerful paradigm. That is one of the most interesting things to me in STAC, is being able to capture this data provenance through all of this, because that has been a serious problem in the scientific community. So now I'm going to talk about STAC background, which is I think what you came here for. So this slide is something I've shown lots before. I think Chris made this originally, and these are all sorts of different geoportals, and this is the way that things were, and this is still largely the way that things are, is that there's a whole bunch of different geospatial portals, and they're backed by different APIs, and every single one of those is different. So this was certainly the case several years ago when Chris organized a group of people and had reached out to me. At the time, I was working at Development Seed with Ian, and we were interested in the democratization of data access and had stood up something called called STAC API for making Landsat data available that was in the public dataset account. And so the idea was to try and standardize what this API and what this language looked like. Now, I put this XKCD comic strip up here because I used to have to explain this a lot, or people would say, well, like why is there a need for STAC? Like, isn't that just going to be another standard when there's lots of additional standards out there? Isn't this kind of reinventing the wheel? And it may seem like that when you first come to STAC, because there's ISO standards and there's all these different standards around describing data, OpenSearch and all that. However, I think that as you learn more, you find that there actually really wasn't a standard out there that does the things that STAC does. It really fit a specific need out there that was sorely needed, and that's why we've seen such great adoption. So back in 2017, the first sprint that was organized by Chris and Radiant Earth in Boulder, right after State of the Map, it didn't even have a name back then. I think that it was just imagery metadata spec. And the requirements, so a group of organizations and people had come out, and the requirements really were to have a search and discovery of geospatial data that was user-centric. It was focused on the user. That wasn't the data provider. That wasn't, it was the people that were actually using the data. So we also wanted to make sure that we were leveraging other standards where appropriate. So GeoJSON was an obvious thing to take advantage of, and I think this was key. GeoJSON is such a great portable file format, and it's standard and it's readable by anything. So having GeoJSON be the standard metadata format for STAC seemed natural rather than something like XML, which I'm sure that people would have complained quite a bit about. Now, it's not a replacement for existing metadata. In fact, STAC, you can put in links to the existing metadata, which might offer a richer or more complete information about, let's say, the calibration or other data that's just maybe not necessarily all that important for users. This also needed to be crawlable so that you could provide metadata, but without having to stand up a service, that you could just make so that somebody could crawl through an entire set of data, and a simple core, but that was extensible. So these were the rough requirements as sort of Chris had laid them out. And the development practices, and this was also really key to adoption and success of STAC, was to implement data and software early on. So that means implementation of data catalogs showing what STAC was, and the software to use it, implement that from day one. So at that first sprint, at the end of the sprint, there was some bit of working software that did something. And then release that early and iterate on that. So this was key because a lot of standards might be developed with a working group where they come up with this whole spec, but they don't necessarily have an implementation of it, and then the implementation is done afterwards. And what you find when you implement these things is you find kind of what works and what doesn't, and it really helps inform the development of the spec. So that was back in 2017. It was about 4 years to a version 1. There was a whole lot of sprints in between. It was a really active few years with a lot of involvement from a whole lot of different actors and sponsors. And I'm sure that I have missed people on this. This was pulled from one of the slideshows a little while ago. It's really been a community effort for sure. And so that's where the STAC spec was born. When we say the STAC spec, we actually mean two different specifications. There is the spec for describing geospatial data, that's the STAC spec. The repo is called STAC spec. And then how to search that data through a RESTful API is the STAC API spec. So you might hear STAC spec, but it really kind of means these two different things, and they're two different repositories. So the STAC status as of now is that it's been now almost a year ago that version 1 was released. The STAC API spec is on a release candidate for version 1. The reason why that is further behind than the STAC spec is because there has been alignment with the OGC features API, and that was not out on a 1.0 version, and that was changing. And so we wanted to make sure that we aligned to that. And so that's why that's a bit further behind than the STAC spec itself. There's a whole bunch of extensions, lots of contributors, and lots of different open source projects in the ecosystem. And perhaps most importantly, we're seeing a whole lot of uptake in catalogs using STAC, both internal and externally publicly available ones. So what's the core specification actually look like? So as I said before, it's JSON or it's GeoJSON in the case of items. It's crawlable. It's a standardization of different metadata fields. So rather than everybody disagreeing on what to call cloud cover, there's a set field. It's called cloud cover _, and it's measured from 1 to 100 as a 0 to 100 as a floating point number. And so those fields. There are 3 different main entities, and actually I should say there's 4 different main entities. I really should add assets here because they are asset catalogs, but there are catalogs, collections, and items. So a catalog is really just a container. It's a JSON file. It's a container that points to other things, other collections, other catalogs. There could be subcatalogs within this directory tree, this tree structure, and then items. An item is really ultimately the main thing of interest because it contains the assets, and that's the 4th thing that's really kind of missing on this diagram and on these bullets. And the assets are the individual files of the data that people are after, or it's metadata as well. Assets are metadata or data. It really could be either one of those things. Collections are a way to group these different items together. An item is essentially a scene, but it's a flexible concept that it could mean a variety of things. But for the most part, it's usually a single scene for a given date time for a specific region. Now, if it's a mosaic, maybe it has a date-time range, but the idea is the same. I said the core spec was fairly simple, the idea being that it would be stable and not change very much over time so that people could rely on a core stable spec. This is really important. So that core spec, this is an item that we're looking at here. Again, the main unit of interest. And we see that this is a GeoJSON feature. It's got some additional fields that STAC adds. We have STAC version and STAC extensions, which I'll get to in a minute. ID, geometry, and bounding box, though, other than the ID, sorry, geometry and bounding box, that is required by GeoJSON. Same with properties. This is where we put all of the different fields like date, time, or cloud cover would go under properties. And then we also have links and assets. Now, they're similar. Well, one thing is links is an array and assets is a dictionary, but the assets are the actual files. These are the data files, or again, the metadata files that are linked to. They have an asset key, they have a media type, and it's actually the thing of interest that users are going to be interested in. Links are a little different. Links are related information or resources. They could be a link to documentation. However, they're primarily used for, like if you're making STAC, make judicious use of links, but their primary use is for that crawlability. And so the links contain, we call them hierarchical links, where you have parent, root, self, child, those sorts of things. Those are hierarchical links, but they could be mixed in there with links to other things, just like the way that the internet works is we have links to other related things, and that's how we can crawl and search the internet, right? So here's a catalog. This is the planetary computer. We go down to a child. This is a collection, and down to that's a collection level asset. And then we go to items for a specific collection. This one here is Aster level 1. And here we have a set of items back, and see how it has links as well. And it has ultimately the assets that we're interested in for this particular item. So now STAC extensions. Chris, I apologize, can't see you. So if you're giving me any warnings about time, you just have to holler out.
I mean, I'm moderating, so I'm going to tell you that, I mean, we're 20 minutes after the hour, which is like that, but like you're also only like 15 minutes into your speaking, if you can wrap it up. a little bit?
All right, I think I can do that and get back on track. Thanks, Renee. Sorry, yeah. Okay. So the stack extensions here. So there's a GitHub organization called Stack Extensions, and it's not all of the Stack extensions that are available. It's really just a clearinghouse. Anybody is really open to coming here and creating an extension for Stack, but you could also just publish one on your own. So for instance, USGS has published a Landsat extension for Landsat specific fields to go into Stack, and they publish that on their own website. But if you wanted to create an extension and needed a home for it, then Stack Extensions, GitHub org is a good one. There are a few, I'm not going to dive into all of these. There's a few notable extensions here that over time have starting to be used in a lot more commonly. So the projection extension and the raster extension, these don't fall under the normal discoverability extensions. Like these aren't adding fields that make things easier to search, or they're things that people want to search for, but they really are there for cloud usability. So by putting in the projection and raster data, we can use things such as Open Data Cube to open up the data and create X-arrays out of them. Other extensions like electro-optical or STAR are really focused on the capturing different fields that are particular to the different sensor modalities. So here's a complete item example. This is a Landsat example from, this really is just an example. It's not from any particular API. So you see we have the properties. There's a bunch of different Stack extensions being used, the geometry. Under links, we have these via links. That's to go back to the original USGS MTL file that was used to create the Stack item. And then ultimately here we have our assets. You see they have a title, you've got roles, you have the href, which is the most important thing, it's that location. And then as we get down into the data, we also have more complex information here. We have classification data so that you know which bits in this cloud mask are representing clouds or cloud shadows. And the data type, and then also when we get down to the spectral bands, we get things like wavelength and the common name of the spectral band. All right, Stack API. So this isn't too long here. These are the former and new OGC APIs. I bring this up because we are aligning the Stack API spec and have aligned the Stack API spec with the OGC API features. So in the top right hand, those are the endpoints that you see from a features API. And what Stack adds is really two main things. One is that root endpoint, that root catalog, is a Stack catalog. It's a fully compliant Stack catalog. And then there's also a search link. And so really the difference between an OGC features API and Stack is the inclusion of these two endpoints and a more restrictive compliant response from the server that gives responses as Stack items rather than a more arbitrary structure. So adoption, back at Phosphor-G, I posted this this tweet about who was adopting Stack and got a whole lot of responses. It was really great to see all the folks responding about how they're using this internally at commercial companies and at government agencies as well. A lot of these have been talked about, so I'm not going to dwell too long on it, but there's several public Stack APIs. There's the Landsat API and CMR Stack, which is really just a proxy to the underlying common metadata repository of NASA that makes it look like it's a Stack API. It translates the queries into Stack, into CMR, and then converts the response into Stack items. The USGS Astrogeology department has been using Stack for the Moon and Europa and Mars, which is super cool. Never even knew that was a possibility, so that was neat to see. And you can go to Stack Index, of course, and see all this has been mentioned several times. I'm going to skip through a lot of these slides because a lot of these software packages are being talked by other people today. But I will call out the STAC Utils organization, which is kind of like STAC Extensions. This is a bit of a clearinghouse for a bunch of STAC related utilities. So a lot of the projects that have been talked about do live here, but it's not the only place. There is other stuff in people's own GitHub repositories, of course. But that's a good place to go to if you're looking to see what's in the ecosystem. I'm going to skip through all of these. It's a bunch of different projects. Stack tools. I guess I should make a couple notes about that. Stack tools is intended to be a high-level repository for working with Stack data, but there's also all these sub-packages, and those sub-packages are specific to data sets to go from the data provider metadata into Stack. And so they're not generally something that most users would use, because once somebody uses this and makes a publicly available catalog, then that's what you would use. But this is where a lot of that work, such as for the planetary computer, this is where a lot of that work is happening, is in these Stack Tools subpackages. Of course, we got the GDAL driver, Stack browser, which Matthias will be talking about, and then Open Data Cube, which is my last thing here. And I do want to call this out. I think this is one of the utilities I find most useful. Open Data Cube has been a library for a lot longer than Stack has been around. But with the development of ODC Stack, rather than an underlying database, we can now point Open Data Cube at a STAC API, and we can turn all of those items into an X-array, and Open Data Cube will handle all of the resampling and reprojection and everything. So it's really great. And I've given some demos, and there's some demos before GitHub using ODC both on AWS and on the planetary computer. And it mostly uses the Pangeo infrastructure to do so, where you're using X-array and then Dask on the back end. And that's all I got. Sorry for going over a little bit there, Renee.
No worries. Beautiful. Thank you, Matt. Next we have